All right, so what we're going to be doing today, we're going to talk about like superposition. So far we learned about KVL, KCL. We learned about like mesh analysis, node analysis, and those are like very general like ways to solve like any circuit. So we have like all those things in the bag of tools that we got to solve any circuits. Another thing that we can add to the bag of tools we have is just a superposition. It is not as general as like a KVL, KCL, or like mesh analysis and loop analysis, or like node analysis, but they're pretty general in the sense that if I have a circuit that is linear, which is basically the subject of this course, so whatever circuit you get as linear, and as long as you have more than one independent source, you can always apply this method to it. So there are like two conditions to be able to like do like this superposition. First, the circuit must be linear. Second, I have to have more than one independent source in the circuit, right? Again, the whole idea of a superposition comes from the linearity. So if the circuit is not linear, this cannot be applied to it. Okay? So let me quickly write down the definition. Superposition is a method that can be applied to any linear circuit with more than one independent source. And the idea behind it is that if I want to apply superposition, since the circuit is linear, I can find the contribution of each source separately, and then to find whatever unknown variable that I have, I can basically add them all up, right? So the idea is to find the contribution of each node and basically find like whatever unknown that I have due to every single independent source that I have. And since the circuit is linear, I can add it all up with its sign and get like the whole output, which is my unknown variable. But how can we apply it? How to apply superposition? The first step is for us to check if the circuit is linear and if the circuit has like more than one independent source. That's the very first step. And as I mentioned, for the sake of this course, all the circuits that we're dealing with, they're linear. So we don't really have to like worry about that part. We just need to like make sure that the circuit has more than one independent source. Okay? So first step, check if the circuit is linear and has more than one independent source. It is important to pay attention to independent source. Okay? I can have one independent and one dependent. I cannot apply this. It has to be more than one independent source. And it should make sense. Why? Because we want to find like the contributions of like independent sources and see, like, for example, if I have like two independent sources, how impactful every single of like those two sources are for our like parameter, whatever we're trying to like find, right? Second step, as I mentioned, is to find the contribution of each independent source. So if I want to find the contribution of every single source, I have to keep one of the sources and get rid of the rest of them. And to get rid of them, what it means is that I have to zero out the rest of the sources, right? So if I have, for example, like 3 sources, I keep 1 source and zero out the rest 2. And I have to repeat this thing like 3 times, right? But what do I mean by zeroing out a source? What it means is that like whatever source I have, whether it's a current source or the voltage source, I have to set the value equal to 0, right? What is a voltage source that has a value 0? What is it? It's just a wire, right? Because there's no potential difference, right? What is a current source with the value 0? In other words, what if I have a branch in the circuit that has no current going through it? What does that mean? It means it's an open circuit, right? So by zeroing out, so how to zero out sources? If I have a voltage source, if I zero it out, it means I have a short circuit. If I have a current source, if I set the value of the current source to 0, it means I have an open circuit. Right? What happens to my dependent sources? Well, keep that in mind. Dependent sources, the value for it, depends on something else in the circuit. So I cannot zero them out. Right? So if I have like a dependent source, it remains unchanged. I'll leave it the way it is. I do not change it. So dependent sources remain unchanged. Now that we zeroed out all the sources but one, now we can use our like favorite method, KVL, KCL, loop analysis, node analysis, to find the parameter that we want, to find the contribution of like that specific source on that specific basically output that we have. So I'm going to call it like 2A, which is use our favorite method, KVL, KCL, mesh, or node analysis, to find the contribution. I have to repeat this for every single independent source I have. And if I find the parameters of it, whatever I'm looking for, V out, I, or whatever, it comes out with a number with a sign. So I have to add them all up with their sign. Right? So solve for unknown variable by adding all the contributions with their sign. Right? So let's do a few examples to see how we can apply this guy. But the whole idea here is that if I have like multiple sources, I can find a contribution of every single one of them and then add them all up. Right? And this is all because the circuit is linear. For those of you who are electrical engineer, you're going to take signals and systems class, and they're going to talk about linear systems extensively. And you're going to see like why this method actually works. But for us, all we need to know is that the circuit is linear. And as soon as the circuit is linear with multiple sources, I can find a contribution of every single source and add them all up. Okay? Let's just do a quick example. Let's just start easy. Example. Let's just say I'm given this circuit This is V1. This is 1K. This is another 1K. Another 1K. And V2. Let's call voltage across this 1K V out. And let's just assume V1 and V2 are given to us. Those are numbers. And the question is asking me what is V out, right? Obviously, this is a very simple circuit. We can do a lot of different ways to solve for V out, but let's just use like superposition, right? If we want to do superposition, we're going to have to look at a circuit. Well, this is a linear circuit, obviously, and it has two independent sources. So superposition can be applied, right? Now that we know superposition can be applied, we have to find contribution of every single source that we have, right? Let's just find a contribution of V1. So contribution of source V1. If I want to find contribution of source V1, I'm going to have to keep V1 and zero out the other one, right? What happens if I zero out V2? It means I have to set the value of V2 0. What happens if I have a voltage source with value 0? It's just a short circuit, right? So my circuit would look like this. I have V1, I have 1K, I have 1K, I have another 1K, and I zero out V2. Let's call voltage across this 1K V out 1, which is the contribution of source, right? What I'm claiming is that we know exactly what this circuit is. What is the circuit? We're very familiar with this circuit. What is it? It's a voltage divider. There's a voltage source there, right? So I can combine these two, right? How? They're in parallel, right? I can combine them. So the circuit basically is this. This is V1. This is 1K. And this is this 1K in parallel with 1K. Right? A couple of quick things. If I look at the original circuit, since V2 is right there, those 1Ks on the top, they're not in series, they're not in parallel, they have no relationship. But as soon as I short V2 out, now those two 1Ks, they become in parallel, right? So it makes my circuit like much, much easier to work with. Another thing I can see is that V out 1 is exactly voltage across this 1K and 1K in parallel. Why? Remember, those 1Ks, this guy and this guy, they're in parallel. So voltage across this 1K is exactly the same as voltage across this 1K, and it's the same as voltage across the equivalent of it. So this guy over here is V out 1. Right? So what is V out 1? Well, 1 and 1 in parallel is half. V out 1, again, as a voltage divider. So it's proportional to the value of the resistance divided by the whole thing times V1. This is 1/3, so it's V1 over 3. Right? Let's find contribution of source V2. So contribution of source V2. If I want to find contribution of V2, what do I need? I need to keep V2 and zero out the rest of the sources I have. So I'll keep V2, which is this guy, and I have to zero out this. What happens if I zero out this? It becomes a wire. right? So my circuit would look like this. This is a 1K, 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 and a V2. And let's just call voltage across this V out. Right? Again, we know what this circuit is. What is the circuit? It's again a voltage divider, right? I can combine these two. They're in parallel. So my circuit would look like this. I have one in parallel with one, which is 1/2. I have this 1K over here. And I have V2. Again, what I'm claiming is voltage across this guy is exactly V out 2. Because 1 and 1 in parallel, therefore voltage across this one is exactly the same as voltage across this one. And it should be the same as voltage across the equivalent, which is this guy. So this is V out. How do I compute V out 2? Again, this is another voltage divider. So V out 2 is 1/2 divided by 1/2 plus 1 times V2. So it's V2 over 3. Right? I found contribution of V1. I found contribution of V2. What is the whole V out? It's just a summation of those with their sign. In this case, both signs are positive. So V out would be V out 1 plus V out 2, which is V1 over 3 plus V2 over 3. But if this one was like negative, then that would have been like V1 over 3 minus V2 over 3. So the sign is carried, right? So the idea is very simple. The idea is that I'm going to find the contribution of every single independent source that I have. Remember, independent source that I have. And to get the whole variable that I have, in this case it's V out, I have to add them all up. Right? Any question on this? Any question on this? Is that clear what's going on? Yes? So let's make it a little more interesting. Just a teensy bit. Let's just say I'm given this circuit. I have a voltage source here, value 12 volts. I have a 3K resistance. I have a 2 milliamps independent current source. I have a 4K resistance here, a 2K resistance here. Oh, let's just say I want to find V out. Right? The first thing I check, the circuit is linear. It has 2 independent sources. I can apply superposition. Right? So to apply superposition, I have to find contribution of every single source that I have. Right? Let's just find the contribution of the 12 volts voltage source. So contribution of 12 volts voltage source. How do I do this? I'll keep the 12 volts and zero out the rest of them, whatever it is. The rest is a current source. So if I zero it out, I have to like open it. So it means there is nothing going on there. So my circuit would look like this. I have a 12 volts. I have this 3K. This is open. I have a 4K. I have a 2K. Let's call voltage across this V out 1. We know V out 1. How? What is this circuit? We know this circuit. What is it? It's a voltage divider, right? If I want to find voltage across that 2K, voltage across it is proportional to the value of 2K divided by the entire resistors times the input, right? So V out 1 again as a voltage divider, which is 2K divided by 2K plus 4K plus 3K times 12 volts, which is 1/3. Right? Is that clear why this is a voltage divider? Because there's nothing going on here. There's no current over here. So there's nothing in here. So I have like 3 resistors back to back. And it's connected to a source, a voltage source. Right? That was our voltage divider. What's the next step? We need to find the contribution of the current source. Right? So let's do that. So I have contribution of 2 milliamps independent current source. To find that contribution, what do? I'll keep the 2 milliamps current source and zero out the rest of them. As soon as I zero out 12 volts, I have to replace it by a wire. Right? So my circuit would look like this. I have a wire. I have a 3K. I have 2 milliamps. And I have a 4K. And I have a 2K. Let's call voltage across this V out. Right? What is this circuit? Again, we know the circuit. It's a current divider. I have a current source in parallel with 2 resistors that are in parallel. Right? So if I call current through here I, what is I? Remember, if I have a current divider, the value of current in this branch is proportional to the value of the resistance on the other branch divided by the whole thing. So it's 3K divided by 3K plus 4K plus 2K times the source. What is the value of the source? Is it 2? It's -2. Look at the direction of the current. The current here is actually going down. But the actual current divider, the direction was going up, and it's split between like those two. So to make this guy going up, I have to make it up by a negative sign. So I have times -2, which tells me that is minus 2/3 milliamps. Now I know current through this. What is voltage across it? What is V out to? I have Ohm's law, right? So I have Ohm's law. That tells me V out 2 is 2K times I, which is 2K times minus 2/3, which is minus 4/3 volts. Right? What is V out in total? It's the contribution of the first source plus the contribution of the second source. So V out is V out 1 plus V out 2. I computed the V out 1 to be 1/3. So I have 1/3 plus V out 2 we just computed it and it's -4/3. So plus minus 4/3. So the whole thing is 4/3 volts. Right? So whatever sign we obtain, it should be carried when we're computing like the total voltage. Any question on this? Any question on this? Is that clear how we computed the V out? Again, I chose to use like those known circuits to make my life easier. You can use whatever method that you want, right? But since these are like very simple circuits, we can like immediately like say, oh, this is a voltage divider, this is a current divider, and then compute whatever we want, right? Any question before I move on? Is that clear why this guy is -2? Yes? Who wants me to explain it one more time? Sure. Let's just have a quick reminder. If I have a current source, which is in parallel with two resistors that are in parallel, if the direction of the current is going up, if I want to find I through R1, for example, I through R1 is proportional to the value of R2 divided by R1 plus R2 times IS. And we call this a current divider. If I compare this to this guy, since the direction of the current is going down, I have to make it go up. How do we change the direction of the current? We put a negative sign behind it, right? So that's how you get this negative sign. Another circuit that we have that is very important, it's a voltage divider. This circuit is a voltage source followed by two resistors. And they're all like back to back, right? So if I wanted to, for example, find voltage across R2, voltage across R2 is proportional to the value of R2 divided by the whole thing times Vs, right? And we said we can actually generalize this to like more than 2, and it would be exactly the same, right? Any question? Let's make it a little more interesting. Let's just say I have this circuit. I have a voltage source with value 12 volts, 6 milliamps current source, a 3K resistance, another voltage source with value 6 volts, a 6K resistor, the whole thing around a 4K. And let's say this time we want to find this I naught. Right? Let's just say we want it. Again, this is a linear circuit. I have 3 independent sources. I can apply superposition, right? So all I have to do is to find the contribution of every single independent source that I have and find I naught corresponding to every single independent source, right? So let's start by looking at the contribution of 12 volts voltage source. So contribution of 12 volts voltage source. How do we do this? We're going to keep the 12 volts and zero out the rest of it, right? So if I keep this and zero out these, what happens to this one? It becomes a wire. How about this guy? It becomes open. It's an open circuit. So if I redraw the circuit, it would look like this. I have this 12 volts. Then this is going to be wire. This is 3K. This is 6K. This guy over here becomes open. And I have this 4K. Let's just call this I naught 1. What is I naught 1? I claim we know exactly what it is without calculating. What is it? Somebody said it. It is 0. Why? Yes. What's happening here is that current always takes the path with the least resistance. So if I have this current going here, it has two paths to get to this point. It's either this or this. So it obviously takes this path with the least resistance. That's one way of looking at it. Another way of looking at it is that these two are in series. Right? You agree with me? There's nothing going on here. So these two are in series. This is the head. This is the tail. If I look at these two as a series that is in parallel with wire, what is the equivalent resistance? 0. So I can replace the whole thing by this wire. So there is not going to be any current passing through here. So I naught 1 is 0, since current always takes the path with least resistance. Another way to convince yourself, again, is to just say these two things are in series, then the result is in parallel with this guy, with this wire over here, right? That's another way of looking at it. So this one was easy. How about the contribution of 6 volts? So let's find contribution of 6 volts voltage source. What do we need to do? We need to keep that 6 volts and zero out the rest of them. If I have a voltage source, when I'm talking about zeroing it out, it means like I got to replace it by a wire. If I have a current source, it means like I have to open it. So my circuit will look like this. I have this guy. I have this 3K. I have this 6 volts. I have a 6K. And I have a 4K. Right? What is I02? Why? No, there is this voltage here. As a matter of fact, if I look at these two, if I combine them, because they're in series, right? There's nothing going on here in this branch, right? Voltage across these two is this guy. Also, voltage across this 4K is this, because they're in parallel. Look. This is the head. This is the head. This is the tail. This is the tail. So these two things, which are in series, they're in parallel with this source. Also, this 4K is in parallel with this source. So I can apply Ohm's law. So what is it? What is I02? It's whatever voltage across it divided by the value of the resistor. What is the voltage across it? What is it? -6 volts. So this is -6 divided by 3K plus 6K, which is minus 2/3 milliamps. If we don't know that, we can write a KVL, right? So second way is to just write a KVL. So if I write a KVL here, what do I have? I have 3K times I02 plus 6K times I02 plus 6 volts. That should be 0. Right? Therefore, I02 is minus 2/3 milliamps. Right? That's another way. Right? Is that clear what's going on here? Is that clear why these two are in parallel with this guy? Yes? Yes? No? All right, so let's just find the contribution of the third source that we have. So we have to find the contribution of this. What's going on? I have to keep this. I have to get rid of these, right? Getting rid of these two means I have to just short them out. So contribution of 6 milliamps current source, my circuit would look like this. I have this, I have the 3K, I have this 6K, I have this current source, 6 milliamps, and I have this 4K. Let's just call this I naught 3. What is this circuit? We know exactly what this circuit is. Let's see if we actually know what the circuit is. What I'm claiming here is that this 4K does not matter. So I can get rid of it. Why? Because let's just call this A. Right? Do you agree this is A as well? Do you agree this is A as well? How about this guy? This is also A. How about this? How about this? How about this? What does that tell me? It tells me this 4K resistor is in parallel with a wire. So I circled back. I started from one node. I circled back to exact same node. So what it tells me is that that 4K resistance is in parallel with the wire. If I have a resistor in parallel with wire, what is the equivalent? It's 0. So I can get rid of it. So that doesn't really matter. Do you agree this is a new node for me? Right? Let's just call it B. Right? Let's redraw the circuit. I have this 3K between A and B. So I have A here, I have B, and I have this 3K here. And what I'm looking for is current. What else do I have? I have this guy between A and B. So I'm going to write it down over here, which is a 6K. What else do I have? I have this guy between A and B. So I have this guy between A and B. Remember, this arrow points to A, this arrow points to A. What is the circuit? What's the current divider? So what is I naught 3? The value of the current is proportional to the value of the other resistance. So it's 6K divided by 6K plus 3K times 6 milliamps, which is 4 milliamps. Right? What is I naught in total? It's just a summation of all the contributions with their signs. Right? So I naught is I naught 1 plus I naught 2 plus I naught 3. We computed I naught 1 to be 0. So it's 0. Plus I naught 2, we computed to be minus 2/3. So plus minus 2/3. I naught 3 is 4. So plus 4. Therefore, the whole thing here is 10/3 milliamps. Right? Any question on this? Any question on this? Any question? Is that clear how this circuit turned out to be a very simple current divider? Who wants me to explain this one more time? There you go. Fantastic. Very, very first thing we notice, look at the circuit. If we name the nodes, it turns out both ends of this 4K got the exact same name, right? What it means is that this 4K resistor is indeed in parallel with this wire right here, right? If I have a resistor in parallel with wire, the equivalent is always 0. We've seen it 2 different ways. First way, current always takes the path with the least resistance. So it's going to take the path with no resistance in it, right? Another way is just a definition of the parallel connection, right? So if I have a resistor in parallel with a wire, first current takes the path with least resistance. Another way of looking at it is just a definition of a parallel. R here is 0. So I have R times 0 divided by R plus 0. That would be 0. That is the equivalent resistor. So what it means is that I can replace this by just a wire, right? So this thing is gone, doesn't really matter. That's basically that point A that I have. Now I'm going to name the rest of the nodes. This is the only node I have that I didn't name, right? And then I'm going to follow like what goes between what nodes. I have this 3K that goes between like A and B, so it's right here. I have this one that goes between A and B, so I have it right here. And I have this current source that goes between B and A. The rest is just a current divider. Yes? Exactly. That's exactly what it means when it's parallel with a wire. Remember, like voltage across a wire is 0. There's no potential difference. That's why we call them like the exact same node across, right? Very good observation. Any question on this? Is that clear what's happening? Should we move on to like another example? Yes? We good? So let's move on. Let's just say I have a circuit that looks like this. I have V1. I have a 1K resistor. I have another 1K. I have a current source with value Vx. I have a 1K. And I have a V2. And let's just say voltage across this is Vx. And we're after voltage across this 1K resistor. Right? Looking at the circuit is linear. It has more than one independent source. We can do superposition. Right? So how many times do I need to just write the superposition here? What are the sources that I need to find the contributions of? There are 2 of them. That V1 and that V2. That dependent current source, we cannot do anything with it. We got to leave it the way it is. And the reason for it is that if you look at the value of that current source, that dependent current source, it depends on the Vx. So it cannot zero it out because it's not 0. Right? So let's just find the contribution of V1 and V2. So contribution of V1. If I do that, my circuit would look like this. This is 1K. This is still Vx. This is 1K. Let's just call it V out 1. I have this guy, which is Vx. I have a 1K. and I have to replace this by a wire. What's happening to this guy? It's just going to be a wire, right? So my circuit would look like this. I have this V1, I have this 1K, this is Vx, this is 1K, and this is Vx, and right here. Let's do loop analysis, right? I can do whatever method I want to find this V out, right? I'm going to write loop analysis. Let's just call it I1 and I2. What I claim is that I know exactly what I2 is. What is I2? It's Vx, right? I know exactly what it is. That's a current source. So I know I2 is Vx. But what is Vx? Vx is voltage across this. What is it in terms of I1? It's 1K times I1, right? So I know Vx is 1K times I1. What does this tell me? It tells me I1 is exactly the same as I2. Right? If I write a KVL in this loop, what do I have? I have 1K times I1 plus 1K. What is current through this guy? That's I1 that's going down. I2 is opposing that, so it's I1 minus I2. Right? That should be V1. Right? But look, I1 is exactly I2. Right? So this term is 0. We know I1 is exactly I2. What is I1 then? It's V1 milliamps. Right? Whatever value the V1 has. V1 and V2 are given. Right? What is V out 1 then? What is V out 1 then? V out 1 is 1K times I1 minus I2. What is it? That's 0. Let's find contribution of V2. Again, I'm going to have to keep V2 and get rid of V1. So what I have here is that this is V1, this is 1K, this is another 1K, this is Vx, this is 1K, and this is V2. This must be 0, so this becomes just a wire. Right? So this becomes just a wire. And let's just call voltage across this V out 2. Right? What I'm claiming here is that let's do node analysis. Again, that's my favorite method of, solving this one. I'm going to call this V2, right? And what I'm claiming is that I know exactly the value of V2. That's this guy, right? These two are in parallel. Let's call this one V1, right? I can write KCL at both nodes. Can I though? Yes, this is a current source. Even though its value is being controlled by Vx, but essentially this is nothing but a current source. So I can write KCL here. So let's assume everything is going out. So KCL at node 1 That tells us that's V1 minus 0 divided by 1k plus V1 minus 0 divided by 1k right here. That's plus Vx, that should be 0. Right? But what is Vx? This is Vx. What is Vx? What is Vx? Do you agree Vx is negative V1? Voltage from here to here is V1. This is positive, negative. So it's negative V1. So I can plug it in here. KCL at node 2. Again, this is going out. But I already know V2, right? I know V2 is this V2. Done. I can solve V1 from here. V out 2 is exactly V1. Then V out is V out 1 plus V out 2. Okay. I now went through like this example like a little bit like quickly. I'm going to go back to it next lecture, but I want you guys to think about it. The whole idea of like this one is that if I have a dependent source, I got to keep it the way it is. All right. I'll see you guys Wednesday.